So welcome back. In the last lecture and the lecture before, I was talking to you about simple harmonic motion. SH. And the last lecture we did part of the study of the energy of simple harmonic oscillators. And just to bring you to the introduction, we had an equation of the kind F is equal to minus Kx, where K was the force constant, X is the displacement. So this is the basic equation of one-dimensional simple harmonic oscillator, and therefore because F is equal to m into d2x upon dt2, therefore x double dot, which is d2x upon dt2, can be written as, and we know it, can be written as x double dot is equal to minus k over m x. Then we found through the introduction of the repeated functions in mathematics, we found that there are four possible solutions for the same equation x double dot is equal to minus k over m x, where one is cos of omega t plus minus plus beta, a cos of omega t minus beta, a sine of omega t plus beta, and a sine of omega t minus beta. They are all equally competent to describe the simple harmonic motion. Of course, a is the amplitude, right, which we found as a star or a naught in the earlier derivation. Now we are dropping that. We are just taking a as the amplitude of the oscillations. Omega is 2 pi nu, where nu is equal to 1 upon t, the time period. Nu is the frequency, angular frequency. K is equal to m omega square from this equation. We are going up like this because k upon m is equal to omega square. And we found, of course, we took this beta as equal to 0 for the sake of simplicity, and we continue with that. So the potential energy part we found was equal to half K A square cos square of omega t, and the kinetic energy we found as half K A square sine square of omega t, and of course I took the equation as x is equal to a cos of omega t. Okay, so the kinetic energy equal to half K A square sine square of omega t, and the total energy becomes equal to this plus this. When I take this half K square as common, I get cos square of omega t plus sine square of omega t, which is the relation which represents the Pythagoras theorem, and that is equal to 1. Cos square theta plus sine square theta is equal to 1. So now let us discuss it further. So I told you that sine of a plus b is equal to sine a cos b plus cos a sine b. Okay. So if I take this 2a, that is a plus a. So for b I substitute a and a. And then I get this equation, that sine of 2a is equal to 2 sine a cos a. I have done it before earlier. Similarly, by taking the equation cos of a plus b is equal to cos a cos b minus sine a sine b, or then if we substitute b is equal to a, I get cos a sine a sine a, cos square a minus sine square. Okay. Now as it is, this is the beautiful equation that we have, which represents the Pythagoras theorem. Cos square of a plus sine square of a is equal to 1, which gives cos square of a is equal to 1 minus sine square of a. Also sine square of a is 1 minus cos square of a. Okay, so there is no problem. It's very simple, it's very easy. Now we rewrite this equation, that cos of 2a is equal to cos square of a minus sine square of a. And if I substitute this value for sine of A as 1 minus cos square of A, then I get finally an equation of the kind 2 cos of now 2 cos square of A minus 1. Okay, so what I get from here, that is 2 cos square minus 1 is equal to cos of 2A. So simply it gives us that cos square of A is equal to 1 plus cos 2A divided by 2. On the other hand, if I write the cos 2A, which is cos square of A minus sin square of A, as 1 minus sin square A minus sin square A, then I get it 1 minus 2 sin square of A. And from there, if I write 1 minus 2 sin square of A is equal to 2 cos 2A, then we get the value of sin square of A as equal to 1 minus cos 2A divided by 2. So I have these two relations, one for sin square of A and the other for cos square of A. I'm sorry, I should have encompassed this one. Okay. And you can check immediately by just looking into the two equations. The cos square of A plus sin square of A is equal to 1 plus this by 2 and 1 minus this by 2. So these two factors go, and half plus half is making 1. Okay. So, with the help of the equation that we took, x is equal to A cos of omega t, I write the potential energy, which is also written as U, the potential energy function U is PE, potential energy is equal to half Ka square cos square of omega t. And this cos square of omega t I will write as 1 plus cos 2 omega t divided by 2. Multiplying, I get 1 upon 4 Ka square plus 1 upon 4 Ka square divided into cos of 2 omega t. And similarly for kinetic energy, which I can write as half Ka square, also as half m omega square A square sin square of omega t. When I take this half Ka square common, then I get it as 1 minus cos 2 omega t instead of plus, and divide by 2. So when I multiply this here, I get two terms, 1 upon 4 Ka square and plus minus 1 upon 4 Ka square cos of 2 omega t. Okay. So I have these two set of terms here. Okay. Now look here. For this potential energy and the kinetic energy, we have got two parts. One part is 1 upon 4 Ka square, 1 upon 4 Ka square. This is time independent. This is time independent. It's not a function of time at all. Okay, this is just a constant. And there is another part which consists of cos of 2 omega t, cos of 2 omega t. So this is a time dependent part, a time dependent. Now, in both the cases, the frequency is 2 nu, because omega is equal to 2 pi nu. So omega is equal to 2 pi nu. Here the frequency becomes equal to twofold. Omega becomes 2 omega, so nu becomes 2 nu. And therefore, look here, the time period associated with the time dependent part of the energy U, and this is also known as K. So we can use this or these two symbols, potential energy and kinetic energy, and we find that the time period of that part, the oscillatory motion associated with the energies, is half the time period of the original function. Okay, we continue with that. So let me elaborate it, and with the help of this time graph and energy graph, etc. You can see that the potential energy U is equal to half kx square, which I can write as, because k is equal to m omega square, so I write half m omega square a square cos square of omega t, which I will prefer to write it as half k a square cos square of omega t. And we found that this is equal to 1 upon 4 k a square plus 1 upon 4 k a square cos of 2 omega t. 2 omega means the frequency is doubled to nu and the time period is halved. Okay. Similarly, for the case of the kinetic energy, I write this expression, which is equal to half mx dot square, that is the velocity square, is equal to, in bracket I am writing again like that, half m a omega square a square sine square of omega t, or simply as half k square sine square of omega t. So it's on the same pattern. Here is the cosine square and here is the sine square, and this also turns out to be equal to 1 upon 4 k square minus 1 upon 4 k square cos of 2 omega t. This part is time independent, and this part is a sinusoid with the frequency doubled and the time period halved. Okay. Now this I can plot as a time graph over here. I take because 1 upon 4 k square, 1 upon 4 k square, this is a constant, so I take it here. This is the 0 and this is 1 upon 4 k square. So this line, the black line over here, it shows that the value is k a square by 4 in either case. With the red color, I am drawing a sinusoid which goes like this. Okay. I have shown the time period to be from, this is the 0 and this time is t by 2, which is the time period, because you can see this has completed one cycle. This was the maximum value and reducing, and the next position is here, the maximum value which is reducing. Also here, so this becomes 2t by 4. This is also t by 2 and this is also t by 2. So 2t by 2. I will not write it, never write it as capital T. It is 2 into capital T by 2, and you should also not write that, because this is the unit in which the graph has been drawn. Okay. So I have almost 3 cycles. 3 cycles of time period t by 2, t by 2, t by 2 respectively. With the green color, I am showing this one. Okay. Minus 1 upon 4 k square cos of 2 omega t. Okay. And this 1 upon 4 k square is as it is. So this goes like this. Okay. The time period etc. is the same. You can see here the time is 0, it's 0 going on positive, and then again 0 going on positive, and then again 0 going on positive, and again 0 going on positive. Okay. So again I can say that from here to here t by 2, here to here it is t by 2, and here to here again it's t by 2. Okay. So when I sum them up, okay, so this is 0, this is the maximum, k a square by 2. Here both are equal, k square by 4, this plus this is k square by 2. Here and here you can see this is 0 and this is k square by 2. So every time what I am going to get is that this curve over here, the black line, this black line is the maximum value associated with frequency. That is, this is giving you the total energy E. So E is equal to U plus K, and we obtain like that. Another plot, another graph, where I show that between the limits, when the oscillation is taking place like this, okay, the kinetic energy becomes maximum when the displacement is equal to 0. It's because the velocity is maximum at that time. Whether going negative or positive, because it has been squared, so this is always a positive quantity. In the case of the potential energy also here, because the value is maximum minus A, so that is squared and all those things, this also turns out to be like this. Both these graphs are parabolic in nature. Okay. So that shows that our harmonic oscillator is oscillating with double the frequency or half this. And for example, I'll just tell you, for those students who know about it, that if I have a rod and I have a choke, sometimes when the chokes are not up to the mark and there are some air particles in between the laminations, then there is buzzing sound. And if we try to catch up and analyze and obtain the frequency, then the AC mains frequency is 50 Hertz. Okay, 50 Hertz. The frequency that we obtain for the sound that is there, and this is because of the dissipation of energy. So energy content, now this becomes from 50 Hertz to 100 Hertz, and there are many condition in which the frequency becomes double and the time period becomes halved. Okay, so these are explained in terms of this. And of course, if you say that I want to plot, say, the equation x is equal to a cos of omega t, okay, x is equal to a cos of omega t, then how it goes? From here to here, here to here, cos of omega t, and therefore we'll say that the plot will go something like this. I'm not drawing that plot because other things will be disturbed, but you have the liberty of using hard pencils, you have the liberty of using the sketchbooks, and you can plot another graph which will show you the original x is equal to a cos of omega t, where the time period will be equal to t by 2 plus t by 2, which is equal to t, and the frequency will be half of this frequency. Okay, this is done and we understand. Now I want to take up a very simple exercise as to know as to what should be the time associated with a displacement like a by 2 or minus a by 2. Let me take it like this, x is equal to a cos of omega. So I write it like this, the t has become t1, and we will determine this t1, calculate this t1. So a by 2 is equal to a cos of omega t1. So cos of omega t1 will become equal to, we divide by a and I will get half. This half, the value is of cos of 60 degrees, and 60 degrees is equal to pi by 3 radians. Then I equate this here, 2 pi upon capital T for omega, and T1 is equal to pi by 3 if I just compare the two phases. The two phases got to be equal, and therefore I find that the half of the value will be obtained at T by 6, because we are starting, if I say it is like this, then this is the 0 value, and this value is obtained at T by 4. This value is obtained at T by 4 into 2. T by 4 into 2. 2T by 4. And this value again is obtained here 3T by 4. And the original value is obtained about 4T by 4. Okay. So this was just a glimpse into what can we do if we are given the value of x and we are asked to calculate the time at which this displacement will be obtained. In the case of minus a by 2, it will be minus a by 2 and this will become equal to minus half, and this will be cosine of 120 degrees, which is 2 pi by 3 radians, and then we obtain that value, etc., etc. So this kind of things you may practice to obtain, and you must understand what I've taken a lot of time. The energy of simple harmonic oscillators has, I repeat and repeat and repeat, has a frequency which is double the frequency nu, and a time period which is half. Therefore, it's obvious that the time period is equal to capital T by 4. Okay, so if the simple harmonic motion, it takes, the time period is 100 millisecond, the time period of the associated part, which is time dependent, will become 50 millisecond. Okay, so I'm sorry, it should not be capital S, it should be small s. The second is represented by small s. Anyway, so we have been able to obtain this thing. Now I will just talk to you about the simple harmonic motion which we obtain with the help of a oscillating body, and which is in a straight line, and it is caused by a massless spring which is attached to a rigid body. I have done that. F is equal to minus kx. Okay. Now I'll just take up, and I think it must be my duty as to tell you how these spring constants are related to in series and in parallel, which is similar to what we obtain in the case of resistances, capacitances, inductances, etc., the combination of them in series and parallel. So I'll take up just now the combination of two springs with the spring constants K1 and K2 respectively. Okay, as I told you, one of the examples of the simple harmonic motion is the mass attached to a spring of force constant K, and when it is given a disturbance x, then this mass starts vibrating or oscillating. Okay, and the motion is simple harmonic motion because F is taken as equal to minus kx. So x double dot, the acceleration becomes equal to minus k over mx, or omega square is equal to km, and many other things which are associated with that. Now what I'm going to put to your feed you is the combination of springs. All springs are always taken as massless, and all these bodies are taken as rigid bodies to which the springs are attached. And here I have got two springs of different force constants K1 and K2. For brevity, I have just taken two of them, and when the force is applied here, an equal amount of force should appear here, a matching force, else there cannot be a stretching or there cannot be a contraction of the spring under consideration. Okay, so what we do is that we consider that the displacement over here is x1, the displacement over here is x2, and the total displacement is equal to x. So I can write the equation is x is equal to x1 plus x2, and if there are many, then x1 plus x2 plus and so on. Now if I take this equation, f is equal to kx, I can write the x, the displacement, as equal to f upon k. Okay, and similarly for x1 I can write f upon k. Remember, both the springs over here are having the same set of force. If f over here, then f over here, and f over here, and f over here, and f over here, so that they are stretched or they are compressed. Okay, so I have this set of equations. X is equal to f upon k, x1 is equal to f upon k1, x2 is equal to f upon k2. Okay, this k2. Sorry, k2. So I have the key equation is x is equal to x1 plus x2. And then I write in terms of f upon k and f upon k1 and f upon k2, and f cancel, so I will get the equation in this form: 1 upon k is equal to 1 upon k1 plus 1 upon k2. And when I solve it for k, it turns out to be equal to k1, k2 upon k1 plus k2, which is product upon sum. If in general we have n springs and their spring constants are, force constants are k1, k2, kn, etc., then we get an equation of this kind, which we have to solve. If all these springs are akin to each other, similar to each other, out of the same bundle, of the same length, then every one of them has got a spring constant k0, k0, k0. And therefore, this is 1 upon k0, 1 upon k0, 1 upon k0 n times. So it becomes equal to 1 upon k becomes equal to n upon k0, or I can just write that the value of the k is k0 upon n. Okay. So there is this is called the series combination. Okay. Well, this series combination is like the series combination of capacitors also. In capacitors also we go like that, and we have and then we get the capacitance C for several capacitors in series. This becomes equal to Cn. If each capacitor has got a value C, then this kind of equation we obtain. Next, let us take two springs in parallel. So what will happen? When the springs are in parallel and there is force is applied over here to the two springs, the forces are split in F1 F1 and F2 F2. Okay, and therefore again write that F is equal to F1 plus F2. The displacement of all springs is the same because they are in parallel. The same x here, x here, x here, like that. So I can write kx is equal to k1x plus k2x, k becomes equal to k1 plus k2x, x goes, and in general I can write it as equal to k is equal to k1 plus k2, etc. And if each of them has the value k star, then this becomes equal to, the k becomes equal to n into k star. So if you need an spring constant of a larger value, then the spring should be put in parallel. And if the value has to be smaller, so in the same way, here we will have the capacitance is equal to n into C0 if so many capacitors. Now I'll just tell you one thing for those students who know about the capacitors and the capacitor combinations and the springs and the spring combinations, why it is that the similar results are obtained in capacitors and in spring, because the energy stored is equal to half Ka square total energy, and the energy stored in a capacitor is half C V square, where V is the voltage. Okay, so because they are both of them are energy storage devices, so therefore their treatment has to be similar, akin to each other. Well, I took this combination in series and parallel because many a question, many a thing you are subjected to this combination just to obtain the master this thing oscillator, which is given by a spring which is massless, rigid body on which a mass is kept, and this there is frictionless surface. This one is a rigid body, and this is what is a harmonic oscillator. So I will deal in the simple pendulum in my next lecture, and I'll just briefly tell you, I'll not indulge in that as to what are the damped oscillators and what are forced oscillators. This thing I can take up later on when many other things, equivalent things in electrical systems are taken in the coming lectures. Thank you very much. I hope you enjoyed. Bye.